In this video, we are going to compare mean of gross measurements, and which were repeatedly measured over a group of girls. Okay, so instead of comparing boys and girls, and today we compare mean of gross measurement between each time point and only using data from girls. So this is the data. Y-axis is a dental growth measure in 10 girls, and these measures are repeated 1, 2, 3, 4 times at age of 8, 10, 12, 14. Okay, and first we want to compare mean of dental growth measure between age 8 and 10 and 10 and 12 and 12 to 14, and see mean dental growth increasing over time. Okay, so in order to compute this p-value, and what is the proper statistical test we should be using? Student t-test? No, it should be paired t-test, right? Because these observations are paired, so we know these two measurements are coming from a same girl, not from two different girls. So we do have to consider this pair in observation. So statisticians make a big thing out of whether your data include repeated measures or not, if it's paired or not. And if you're measuring more than once from one sample, or if you're measuring one time from each sample, why do you think they are so sensitive about repeated measures? And because all classical statistical techniques assume data used in analysis are independent to each other. So when you look at your analysis, so in this case, okay, so this is the data we are going to use today, and you can tell if the data set include repeated measures by checking if you have one line coming, more than one line coming from a single patient, then your data contain repeatedly measured observations. So here we have 4 lines and then measuring for the same subject, so we know data are repeated. So when you ignore this repeatedness and conduct analysis such as student t-test, and your analysis will be biased. Why is that? And p-value is a probability. So simple questions. Let's compute the probability of randomly chosen 2 people in our classroom will move to Atlanta next month, assuming each of us has 10% chance to move to Atlanta next month. Okay. So you might think it's 10% times 10% and 1%. So what is happen if the probability, if you know what will happen in this probability, if you know the 2 people who are chosen are married, okay, instead of randomly picking 2 people and then calculate probability of both of them moving to Atlanta, and you know these 2 people are married, and then what would be the probability these people are moving to Atlanta? And in this case, probability would be probably close to 10% instead of 1%. And because if the husband moved to Atlanta and wife is likely to follow him, or if wife moved to Atlanta, husband is very likely to follow her, and then the probability both of them are moving to Atlanta is close to 10%. And so probability computations are very sensitive if to the fact if 2 measurements are related or not. And therefore we are so picky about choosing statistical test. Depends on if the data are related or not related. So repeated measures and measurements coming from a single patient are very similar. So therefore you can't really treat those data as these data. Okay, so the gross measurement coming from a same girl is very similar. So if you ignore that similarity or dependence correlation, and that will bias your p-value computation. So this is a list, and I use similar list in basic statistical class, If you haven't seen this list, then please watch the video how to select proper statistical test. And so when we select proper statistical test, in first question we ask whether the analysis is univariable and multivariable. Second question, are you looking at difference or correlation? And then third question is asking, is a data paired or unpaired? Okay? And if you answer paired, choice for statistics are totally different. So instead of using student t-test, and you use paired t-test. Instead of using one-way ANOVA, and you use mixed effect regression. Instead of using Mann-Whitney U-test, and you use Wilcoxon-Sain rank test. Instead of using Kruskal-Wallis test, and you use Friedmann test. And instead of using chi-square test, and you use Mach-Nehmer test. And so we have to be very sensitive and to judge whether the data are independent or coming, if there are multiple observations coming from a single patient. So let's analyze this data. So we know we can't use student t-test, so we use paired sample t-test. So let's do that together. And to do paired sample t-test, it requires horizontally entered data. So we need to go to this horizontal data set. And so let's do paired t-test. So we are only comparing within the girls. So we will select data only from girls. So let's make sure we are selecting out boys. Okay, good. So we have 10 girls. And then we are comparing whether gross measurement at age 8 is different from gross measurement measured at age of 10. And also compare 10 years and 12 years, and also 12 to 14 years. And you go to, if you do paired t-test, you go to compare means and paired sample t-test. Okay? And then you do 8 and 10, so this will compare 8 and 10 years. And then 10 to 12. Okay, so this is another paired t-test, compare measurements between 10 and 12. And then another paired t-test to compare measurement between age 12 and 14. And then click OK. Alright. So when you compare 8 and 10 years and p-value is 0.004, when you compare pair 2, which is 10 to 12 and p-value is 0.049, and when you compare 12 to 14 and p-value will be 0.004. And if you repeat this analysis with nonparametric, and you go to nonparametric test, independent sample, not independent, sorry, and we have to go to nonparametric and related samples. Both you enter 2 tests at a time. So if you do 8 and 10, okay, so this is a p-value. And if you do, you have to go back again and then repeat this to 10 and 12, and you can do so this is not Mann-Whitney test, this is Wilcoxon-Sain rank test, and p-value is 0.031. Okay. And then again you repeat this to analysis comparing 12 to 14. So you can do nonparametric tests for paired data. And let's go back to the lecture note. As you see, when we compare age 8 and age 10 within girls, then p-value is 0.007, and with Wilcoxon-Sain rank test, which is a test to consider pair, 10 and 12, and p-value is 0.031, and 12 to 14, and p-value is 0.014. And if you mistakenly ignore the nature of pair in the data, or nature of repeatedness in the data, and your p-value would be much larger. So 0.0191 between 8 and 10, 0.418 between age of 10 and 12, and 0.315 between age 12 and 14. And let's make sure this is not because we are using non-parametric test. So if we change this to parametric test of t-test, paired t-test, which is a proper test to consider pairedness in the data, and p-value is all significant between 8 and 10, 10 and 12, and 12 and 14. And although if we use independent sample t-tests, p-values are all insignificant. And so when we use tests which consider paired nature of data set, i.e. repeated nature of data set, i.e. dependency among data set, i.e. with p-values are much smaller. So let's consider why this difference is happening. And which method do you think more appropriate than the other? Okay, so we know the method which consider pairedness, relatedness of data is more accurate. So in this case, we would use paired t-test or Wilcoxon signed rank test. And comparing means of growth measure between age 8 and 12 ignores the fact that measures within the child are similar. The test ignoring the fact that measures within a child are similar, dependent, related, pair, which violate independent assumption of student t-test or independent sample t-test. Okay, so therefore we know we can't use independent sample t-test or Mann-Whitney U-test. And then rather than comparing mean of growth measure between age 8 and 10, and we should, rather than using independent sample, the same thing as student t-test, independent sample t-test, and we should use paired t-test. And what in fact paired t-test is doing is, instead of comparing mean of age 8 and age 10, and it's taking within patient difference. And then the mean of that difference is 0 or not. Then paired t-test compare whether the mean of within patient difference is equal to 0 or not. And so what it is doing is and instead of directly comparing mean of gross measurement at age 8 and age 10, what it is doing is it take a difference between 10 and 8 within each patient. So if this patient difference delta is this much, okay, and if you're looking at this gray line, and difference is this much, okay, and if you're looking at this green, and difference between 8 and 10 is this much, and if you look at the red, difference between 8 and 10 is this much, and purple, difference is this much, blue, difference is this much, and again dark blue, difference is this much, and darker blue, difference is this much. Okay. And so what the paired t-test did is it took a mean of this within patient difference and then conducted statistical test to test whether the mean of this within patient difference is equal to 0 or not. Okay, so paired t-test did not really compare mean at 8 years and 10 years. And instead, what the independent sample or student t-test is doing is it took mean at 8 years of age, and then look at this. Mean at age of 8 years has this much variation of data, and then mean of 10 years of age has this much variation of data. And so student t-test, if you look at the formula, okay, and this is the variation, standard deviation, put standard deviation between 8 and 10. So bigger the between patient difference, of course this standard deviation is larger. Now, although if you look at within patient difference, okay, and standard deviation is much smaller, because by taking a difference within patient and between patient difference actually is getting cancelled out. Okay, so you don't have to worry about variation among patients. Your analysis only focus what happened within patient. Okay, and so by using within patient difference, which is another summary measurement, okay, and we actually eliminating between patient difference, therefore analysis focus what happened within patient. And one sample and a paired t-test is one sample t-test assessing whether within patient mean is 0 or not. Okay, and so that analysis has much better precision. Okay, so again, let me repeat. A paired t-test is a summary measures approach, and because it creates a measure to summarize to repeatedly measure data for each patient by one number, which is a difference between before and after, or age of 8 and age of 10. And then apply simple statistical test, which is one sample t-test, which compare whether within patient difference is average is there 0 or not. Okay? And it makes statistical comparison simpler and a lot more intuitive. So this did not paired t-test is not the complex statistics. It's simply one sample t-test comparing within patient difference equal to 0. So when do you think we gain more power by conducting paired t-test? As you see, when the data has a lot more patient variation than a variation within patient. Okay? And so by using within patient difference, it eliminates this large between patient difference. Therefore, paired t-test gain power. All right? So let's learn new terminology. Intraclass correlation coefficient. General term for that is correlation. So correlation between two measurements. So in this case, dental growth measure between age 8 and age 10. And you can say correlation is much greater when you have a lot more between patient variation than within patient variation, because correlation coefficient, in special terminology for that, is intraclass correlation coefficient. ICC is really the ratio between patient variation and divided by total variation, which is between patient variation plus within patient variation. So therefore, when the between patient variations is a lot larger compared to within patient variation, and then you can say there is a high correlation. So this data and correlation between dental growth measurement between age 8 and 10 years old is 0.87. And comparing this data to the other example, this is CRP data and took months between 1 and 2 among chronic kidney injured patients. And correlation is 0.52. So you can see a lot more within patient variation than between patient within patient variation than this example of dental growth measurement. Okay. And inflammation marker is a lot more unstable. Therefore, within patient difference is as large as between patient difference. Okay. So let's go back to this paired analysis. So here is the story we have. And when we compare dental growth measure between age 8 and 10, and difference is 0.007, and 10 and 12 difference 0.031, and 12 and 14 difference is 0.014. Let's look at what the story we got. So when we compare dental growth measurement, mean of dental growth measurement between age of 10 and 8, difference is significant. 10 and 12 and difference is also significant, and 12 and 14 difference is also significant. And although there is a problem with this analysis because multiplicity. So we have p-value, 3 p-values. So you might be told you cannot really use 0.05 to consider statistical significance. And again, we do need global test, which simultaneously assess these 4 means, if they are simultaneously same or not. What is that kind of test? ANOVA, yes. So we had to do ANOVA type test. And now we can't really use ANOVA because data are related. So what do we have to do? Okay. So if we stick with nonparametric test, and there is actually type of test that we can use to compare related multiple means from related data, which is Friedmann test. Okay. So if data are not correlated, are not related, not measured from the same group of patients, we could use Kruskal-Wallis test or one-way ANOVA. But since these data are related, we cannot use such tests. Instead, for Mann-Whitney test, for nonparametric test, we can use Friedmann test. Friedmann test is brother or sister to Kruskal-Wallis test. Only difference is Kruskal-Wallis test assume independence among 4 means, 4 groups, but Friedmann test allowed to have repeated measurements, dependency among those 4 means. Okay, so in this case, when we compute Friedmann test, okay, so let me do that, and you require horizontal data for that. So let's go to nonparametric related samples, right? And let's put all 4 in test fields, and then click run, and this provide Friedmann test, okay, and which is Friedmann test and less than 0.0001. So, and we detected global difference, and therefore we are allowed to report this p-value without multiplicity adjustment. Okay, so we say Friedmann test is brother or sister to Kruskal-Wallis test, which is a nonparametric test, but you can use for related means. And so next we will talk about what if we want to adjust for something, then nonparametric test can adjust right? So we have to now jump to regression. Okay, if data are not related, we could use linear regression or ANOVA, but we can't because data are related. So choice for the regression is mixed effect model. Okay, so we are going to use mixed effect model. SPSS call it mixed model. I like to call it mixed effect model. So we are going to mix model and linear, right? So what we are going to do is we will repeat this analysis similar to Friedmann test, but now test is for parametric. Okay, so mixed effect test is similar to one-way ANOVA. So if you go back to this original table, right, and if you have dependent data, and instead of one-way ANOVA, you do mixed effect model, and instead of Mann-Whitney test, you do Wilcoxon sign rank test. Instead of you do Kruskal-Wallis, you do Friedmann test. Okay, so mixed effect regression is brother or sister to one-way ANOVA, and although now we can use repeatedly measured data. Alright, so in order to do mixed effect model, it requires longitudinal format. So you have to go to gross_long data set. Okay, this one, right? So we're still using data only from girls, and we want to compare mean of growth measurement is different among age categories. So we go to mixed models, linear. Okay, and subject, and we put indicator to show who is who. So that's ID, and repeat, and we are repeatedly measured over different age. So age will go under repeated box. And then here there are many choices for repeated covariance type, and I will explain what the covariance type means. But for now, let's use unstructured. In setting unstructured, and result of your analysis would be the same as paired t-test. Okay, again, we are talking about parametric test for paired data. So you click continue, and then dependent variable, it's growth, and then the sex, we don't need to worry about sex because we're using only girls for this data set. So age will go under factor. Okay, and click fixed. And then age, you have to move to this box under model and click continue, right? And then click statistics, and we want parameter estimate. Okay, otherwise SPSS doesn't give you beta coefficient. And I think we're ready to run. Alright. Okay. So this p-value under type 3 test for fixed effect, and this p-value is equivalent with ANOVA p-value. So this is testing whether the mean of gross measure are all the same at 4 time points. Okay, it's rejected. Therefore, you can say at least one mean is different from another. Right? So now you are allowed to look at each pair. So again, when you look at the estimate of fixed effect, and here we can tell the reference category is age. So here this estimate -3 is comparing age of 8 to age 14. And the -1.75 is comparing age 10 to 14. And -0.95 is comparing age 12 to 4. And results are all significant. Okay, and if you want to do all pairwise, and you can go back to mixed model and then click on EM means. So this is where you can do multiple comparison, multiplicity adjustment. So you have a choice of LSD, that means no adjustment, or Bonferroni or Sirax method. It's the same concept we learned in one-way ANOVA. Okay, and since global test detected significance, so we are not going to adjust for multiplicity. Okay, and we want to set the reference category to the age of 8. So change. Alright, and continue and OK. So then you have all three pairwise: age 10 and 8, p-value 0.004, 12 and 8, p-value is 0.000, and age 14 to 8, p-value less than 0.001. In fact, it's unlike a one-way ANOVA. SPSS is only giving you comparison to reference category. So if you want to compare 10 and 12, 12 and 14, you actually have to repeat this analysis by changing reference category. So if you want to change your reference category to age 10, and you go back to EM means, and then highlight age, and then you click on custom and change value to 10. And if you want to compare between 12 to 14, you change this value to either 12 or 14. Okay, so you can basically get all pairwise comparison. And let's go back to lecture note. And this slide gives all comparison to all category as a reference category. Okay, and so 10 and 8, p-value 0.004, and 10 and 12, p-value 0.049, and 12 and 14, p-value 0.004. And these p-values are in fact same as paired t-test. Okay, so good thing about doing mixed effect model is now you have a test for global comparison, so you can simultaneously compare all four means are the same or not, and then if it's rejected, and you can avoid multiplicity adjustment. Okay, so this is the final story for this analysis. Okay. And here I added 3 more pairwise, so you can have up to 6 pair test. And I'm not going to adjust for multiplicity because global test is less than 0.001. Again, when you have too many pairwise comparisons, and then I'm not sure if global test assure the protection for type 1 error. So again, it is better to have a fewer number of groups to compare anyway.